All right, hello everyone. This is, I believe, my last lecture. So we will talk about more about moment tensors and also about source time functions and stuff like that in earthquake sense. So we were talking about non-double coupled moment tensors. And one type that I'd like to draw your attention to is compensated linear vector dipoles, CLVDs. And these are 3-4 dipoles with one dipole minus 2 times the magnitude of the others. So the trace is 0. So there's no isotropic component. There's no explosion or compressional component. And these occur rarely, but they are observed in complicated tectonic environments. So one possibility is that in volcanic areas, an inflating magma dike can be modeled as a crack opening under tension. And so from Aki and Richards, which is a book called Quantitative Seismology, it's sort of the Bible for seismologists. Once you've had an introductory seismology course, the Aki and Richards book will come in handy. Anyways, the moment tensor for such a crack is lambda, lambda, lambda plus 2 mu. And the trace is non-zero because the crack opened. So you can decompose the tensor into 2 terms. One is an isotropic component, and the other one is this component here. So what could be happening is we have an eruption, and then deflation of the magma chamber causes the central block here to move downwards. And here are some examples of focal mechanisms, and we'll talk about these more shortly, but that are observed in around Iceland, where there was a volcanic eruption. Another alternative is CLVDs are due to near simultaneous earthquakes on nearby faults of different geometries. So we have one fault that creates a moment and a double couple, and then another fault that also creates a double couple. And if you add them together, then you get one component of our moment tensor is minus 2 times the amplitude of the other 2. So, and this gets me to interpretation of moment tensors. In reality, they never look like pure double couples. So a pure double couple, when the moment tensor is rotated into its principal components, should just have lambda 1 and lambda 2, and lambda 2 would be negative of lambda 1. In practice, this is not usually the case. So typically we have lambda 1, which has an absolute value that's greater than the absolute value of lambda 2, which has an absolute value greater than that of lambda 3. In most cases, lambda 1 is almost equal to negative of lambda 2. So this is the sort of normal double couple. And then lambda 2 is greater than lambda 3. But the fact that there's a lambda 3 at all suggests that it's not exactly a double couple. So one thing we can do is decompose our observed moment tensor into an isotropic component and a non-isotropic component. And then what we would do is separate the deviatoric tensor, which is the non-isotropic component, into major and minor double couples. So lambda 1 and minus lambda 1 are the major double couple, and minus lambda 3 and lambda 3 are the minor double couples. So this minor double couple is thought of as faulting on a separate fault or just noise. So usually the magnitude of the major double couple is much larger, and we treat that as the earthquake source mechanism. So if you were actually doing a observations of a moment tensor, you would probably come up with lambda 1, lambda 2, and lambda 3. You would remove the isotropic component, and then you would take the remaining tensor and separate it into the major and minor double couples. So here's an example. This is in units of 10 to the 27 dyne centimeters. So normally I would work in Newton meters, but this is actually from the Stein and Weiss session book, and they do things in dyne centimeters. So here they haven't removed the isotropic component, but what they have done is diagonalize the matrix and then separated it into the major double couple and minor double couple. And the eigenvectors of this major double couple are N1, which gives the p-axis, of the double couple. N2 gives the t-axis, and N3 gives the null axis, which is perpendicular to N1 and N2. And since this is actually something we can convert to a fault plane using something we learned in the previous lecture, then we can convert this into thrust on a fault plane, striking north 189 degrees east and dipping 23 degrees to the west. Now, a moment tensor decomposition is non-unique. So we could also decompose this into a double couple and a CLVD. So here is the double couple, and then here is the CLVD. And the relative strength of the double couple compared to the CLVD is given by the ratio of the smallest and largest deviatoric eigenvalues. So lambda 3 prime over lambda 1 prime. So if E equals 0, if lambda 3 prime is 0, then we'd have a pure double couple mechanism, and E equals plus or minus 0.5 shows a pure CLVD source. So at Harvard, they automatically calculate the moment tensors for larger earthquakes, and they keep a catalog of that. And about 4% in the Harvard moment tensor catalog have epsilons of greater than 0.3. So some of these may be artifacts of the inversion process, similar to spurious minor double couples, and some appear to be real source effects. So again, I'd say that decompositions are non-unique. So if we have lambda 1 prime, lambda 2 prime, and lambda 3 prime, we can decompose it into this major and minor double couple, or this major and minor double couple. Now, typically, we would try to minimize lambda 3 prime or well, lambda 2 prime as well. So our goal would be to figure out which decomposition creates the smallest moment values on your minor double couple. All right, so in terms of moment tensors, and what we've learned in the previous lecture was we started out with elastic rebound theory, and I showed some earthquake photos. And then we talked about the Green's function, which describes the deformation at a point in time for a given impulse at another point in time. These are linear, so the effects of multiple forces can be summed. And then we use that to derive moment tensors. And moment tensors can be rotated into principal axes. And that gives us components only on the diagonal of the tensor. And the eigenvectors of that principal axes, well, any moment tensor gives the p, t, and null directions. We talked about double couples, but we also talked about isotropic and Clbd components. And then we looked briefly at decomposition. Finally, I would emphasize that the scalar moment is equal to mu, which is the shear modulus, times d, the distance the fault is slipped, times a, the area over which the fault has slipped. So with that in mind, I'd like to talk about radiation patterns and beach balls. And this is chapter 4.2 in Stein and Weiss session. It's also chapter 9.3 in the Peter Shearer book, which is a nice complement to Stein and Weiss session. So what we've done is we've taken the slip versus time rupturing of an actual earthquake. So the rupture surface is irregular. Different parts of the rupture surface rupture at different times, and the slip on the rupture surface varies. So we could have slip over one point be 3 meters and slip over another part of the rupture surface only be ½ a meter. So we've taken this and we've approximated it as slip along a plane. And this allowed us to produce the equivalent double couple. And that can be described by a moment tensor. And then when rotated into its principal axes, we can also calculate the scalar moment, which equals mu times d times a. Again, mu is the shear modulus of the crust that's deformed. D is the length over which the fault is slipped, and a is the area of the fault that slipped, so the area of this plane here. So now I want to talk about how energy radiates outward from a fault and what the amplitudes are of S and P waves as a function of orientation from a fault. And then I want to use focal spheres to indicate the type of faulting and direction of faulting that occurs. So we will recall that for a point force, U of I is equal to G of ij times F of j, where G of ij is the Green's function, and F of j is the impulsive force that leads to deformation of U of I. So a while ago, we saw that the solution to the inhomogeneous P-wave equation with the source time function, actually, we didn't cover this, I don't think. So the solution to the inhomogeneous P-wave equation with a source time function of 4 pi delta, this is the Dirac delta, times f of t, is going to look like this. So here's the homogeneous P-wave equation, and then the force here is put on the right side. And we can solve that, and we get a P-wave potential that varies with r, where r is the distance from the source. So we can take the gradient of the scalar potential, which is how we get at the deformation. And since phi only varies with r, this just involves a derivative with respect to r. So our displacement is a function of distance and time is just going to be dr, d phi dr. And when I do that, I get a near field term of 1 over r squared f of t minus r over a. And this reflects permanent displacement at the source. And I also get a far field term, which is 1 over r df dr. And that is going to be dominant at long distances, but it will just be transient deformation. So this is, these are the sinusoidal waves that propagate by seismometers, but they don't cause permanent deformation. Whereas this here is actually permanent deformation. So let's look at the far field motion. And I won't derive it, but we can say that U of I for a P wave is equal to 1 over 4 pi density times alpha cubed, where alpha is the P wave velocity, times sine of 2 theta cosine of phi times 1 over r, the time derivative of the moment tensor in the r hat direction, so the direction outward from the source. And this is the far field P wave radiation pattern, and it looks like this beach ball here. So we have areas where deformation is compressional, which is outward, and areas where the deformation is dilatational or inward. Some things of note: there are 0 amplitude planes, so shown by these green dashed lines here. These are nodal planes. Amplitudes are the maximum at the center of each quadrant, so between each nodal plane, amplitudes are largest. And the convention is to shade the quadrants where P wave particle motion is compressional. So this here and this here are giving compressional motion. We can do the same thing with S waves far field deformation. And in this case, things are a little bit different. So here we're continuing to shade in the P wave deformation, but superimposed on this, these arrows show the S wave motion. And what we see is at the pressure axis, we have 0 S wave deformation, and it's maximized on the nodal planes for the P waves. And again, it's minimized at the tension axis and the pressure axis. So the S waves are perpendicular. The deformation is perpendicular to R. So it goes around the circle rather than away from the circle or into the circle. So at the source, we experience tension where in the far field we have the compressional quadrant, and we experience compression for the quadrant that has tension. So where I have compression, we have local tension. So in the near field, we have local tension, and in the far field, we have compression. And here in the far field, we have tension, and in the near field, we have compression. So this is shown by the tension axis and pressure axis. A useful way to understand and look at the orientation of fault is to map out the polarity of the P wave first motions around an epicenter. And then we calculate the ray geometry for each observation. So if I have an earthquake at this hypocenter, we calculate the takeoff angle given an observation at this station. And then we back project the ray to a small sphere surrounding the earthquake, taking into account the angle of inclination and the ray's azimuth. And then what we do is we look at the bottom hemisphere of the sphere, and for these seismometers shown by these upside down triangles, we record on this focal sphere the first motion, whether it's compressional or dilatational. So here's another example. So here's the earthquake, and we look at the lower hemisphere here, and then we record whether the first motion observed at these seismic stations are compressional or dilatational, and then we plot it on this focal sphere. So here's a close-up of a focal sphere, and for earthquake C and D, I don't know why there's two C's here. Oh, this is compressional and this is dilatational, that's why. So for this earthquake here, we observe dilatational first motion. For this earthquake here, we observe compressional first motion. And what we do then is we color in the area of our focal sphere that has compressional first motion, and then we leave the areas where there's dilatational first motion to be white. So here are some examples. This is a thrust fault. This is a normal fault. This is strike slip fault. And we can see the first motion here is just barely compressional. It's dilatational here. It's kind of not doing anything here. Here it's first motion compressional and so on. And so with enough observations, we can create a accurate focal sphere. One way we can do this is using a stereo net, but we won't go into that here. But it is useful to get an intuitive feel for these beach balls. So I think of the lower focal hemisphere as a spherical bowl or salad bowl that one is looking directly down on. And then this here, so I'm looking in map view, so I'm looking down on this bowl, which goes into the earth. And the black part shows where the motion, the fault motion is away from the hypocenter. And the white parts show where the first motion is towards the hypocenter. So a thrust fault has first motion away from the hypocenter at the near vertical incidence, whereas a normal fault has motion away from the hypocenter at much shallower angles. A vertical dip slip is going to look like this, and a strike slip fault, so we would have first motion in this direction and this direction, would have compression on either side of the strike slip fault and then dilatation. So here are some more examples. What I would suggest is that you look at this and try to intuit how this fault or this fault, because these are equivalent. One is the auxiliary plane and one is the actual fault plane, and we don't know which one is which, how these two faults would lead to this sort of focal mechanism. And with this in mind, we can see plate tectonics in action. So here we have a strike slip fault. This is the San Andreas fault. Here we have a subduction zone. So we have compression and a thrust fault. Let's see here. Here's a normal fault, and so on. So we've calculated the far field radiation pattern for P and S waves. We will try to remember the features where the P and T axes are. So the P axis is in the center of the dilatational field. The T axis is in the center of the compressional field. We've also looked at the P wave and S wave far field motion as it varies with angle. So for instance, we can see that amplitudes are largest away from the nodal planes and smallest on the nodal planes, at least with P waves. With S waves, it's just the opposite. However, that I would note that this shaded in area is showing the first motion compression due to P waves, not the S waves, because S waves don't really lead to compression or dilatation because they're going side to side. They're actually following the sphere rather than going outward or inward. All right, any questions on that?
Dr. Schutt, I have a few questions.
Yes.
So what is the physical meaning of CLBD?
Well, we're not really sure. It does seem in some cases that it is due to a magma chamber that has contracted. So you have an eruption and then you have a slug of the volcano that's actually moving downward. In other cases, it does seem to be just two simultaneous earthquakes that just happen to occur at the same time. And other cases, it's just noise. And then in other cases, it's really not known.
Okay, so you showed us I think the beach ball for CLBD would look like a dark spot or like a black circle or what? I mean, because energy is radiating in all directions, right?
Yeah, it's like a dark spot or a light spot. It's a circle on the moment, the focal mechanism diagram.
Okay. So we already had that for like a nuclear bomb blast or some other types of, for example, a meteorite impact. So,
well, in the case of a nuclear bomb or meteorite, it would be all black.
Okay. And in case of CLBD, it would be, what would be the difference between that and this beach ball? I mean, how different would it look?
So a CLBD would look like, let me show you here. Here's a CLBD. So it's got a black circle surrounded by a white circle, whereas a nuclear bomb would be completely black.
Okay. So there's compression in the center and tension outside. That's why CLBD. Okay, you said epsilon greater than 0.3 in the Harvard slide. Could you please explain what it means?
So if epsilon is 0, we have a normal double couple. If epsilon is greater than 0.3, we have a significant CLVD component to our moment tensor. So that I was just saying that 4% of the calculated moment tensors seem to have a CLVD component. So it's rare, but it is observed. And in some cases, this may just be noise, but other cases, this may be physically realistic.
So this could be a volcano just a few kilometers underneath us. That's what it means. I mean, why is understanding CLVD this important? I mean, is it because we are looking for a volcano, or what is that? Or we are looking for two faults?
Well, I think it's interesting because it's unusual. So in places where there is no volcanism, then it can't be volcanism, and then it could be two simultaneous earthquakes, for instance.
But two simultaneous earthquakes means there are two different faults where slippage is happening. But that happens all the time, right? That happens all the time because near San Andreas, there are auxiliary faults along the main fault. And when slippage happens on the main fault, the auxiliary faults also slip. So that is happening all the time, right? So what does two earthquakes mean?
Yeah, so usually we get aftershocks that are distinct from the normal shock. But in this case, the normal shock and a smaller aftershock occur roughly at the same time. So that's actually fairly unusual, that you can't distinguish the two.
Okay, I see. So it's about the timing, the sequence of events, not the event itself, right? Okay.
Yeah.
Okay, I'm good. Thank you.
All right. Any other questions? All right, I will just jump into the next lecture then. Oops, not this one. There we are. All right. So, what I've talked about to you about in terms of moment tensors and Green's functions, and what I will talk to you about the seismic source are certainly things that you could have a whole class on. So we are making a lot of, I'm giving you brief descriptions of things that are much more complicated and we could go into much more detail. But that's fine. So my final lecture, I want to talk about the seismic source, which is section 4.3 in the Stein and Weiss session book. So first, I want to consider what is recorded at a seismometer. So there's a source, so the earthquake itself, and that's going to vary in time. The energy travels through the earth and it's modified by earth structure. It's attenuated a certain amount, and then it's received by a seismometer, which does not record the energy perfectly. So because the earth can be approximated as a linear time invariant system, and if you take a time series analysis class, they would get into this, these multiple effects are convolved with each other. So our observation, our deformation observed is S of t convolved with E of t, convolved with Q of t, convolved with I of t. And in the figure, E of t and Q of t are put together into Q of t. And so our source, our structure, and our instrument would lead to a seismogram. And you can note that the seismogram records something that looks quite different from the source time function. So we actually have to remove the structure effects and the instrument effects from the seismogram before we could even get at the source function. Now in the frequency domain, capital U of omega is the product of the Fourier transforms of these four functions. So it's often easier to work in the Fourier domain because then we can just divide through. So if I want to know the source function as a function of frequency, I can take the observations as a function of frequency and divide through by the earth function, the attenuation function, and the instrument function. In many cases, the response of the earth will have frequencies for which there is zero energy. So this denominator would go to zero for certain frequencies, which would cause our source function to blow up. So there are ways to deal with this. In some cases, it works out better to stay in the time domain, but also we can add a certain amount to this denominator so that it never goes below a certain amount. It reduces the resolution of our source time function somewhat, but it does have the benefit that the source time function doesn't blow up as well. So I want to first look at the Earth's response. So the Earth's response is going to be the bounces off the various interfaces. So if the first 30 seconds of this P wave seismogram will be a P, a little p big P, and a little s big P. Each phase will have different amplitudes due to the radiation patterns. And the different phases will react to the interfaces differently. Oops. So we might have a P wave with a positive energy and little p big P and little s big S. Because they bounce off the surface, they're going to have a negative energy or a negative reflection coefficient. And so our seismogram is going to look something like first motion up and then second motion down. The waves have variable arrival times, and we can typically model this by a series of impulse responses. So we can predict the arrival time of the P, little p big P, and that little s big P. We know all about intrinsic attenuation already, so I won't go into it in any great detail. And also I'd like to talk about the instrument response. So a long period seismometer is actually not going to measure things perfectly accurately. This is actually for an older type of seismometer. For a newer seismometer, their gain is pretty flat over a long set of wave periods. But the important thing to note is that if I look at the impulse response of a seismometer, so an impulse response is the response that the seismometer records when the input is a spike function. And this is not a spike function. So it actually modifies the waveform somewhat. And we can look at this in terms of the gain and the phase. And we can see over a certain area, the gain and phase is quite flat. But then as you get to lower frequencies or higher frequencies, then we start to have what we call corners, basically, where the gain and phase vary fairly substantially. And up until now, we've represented slip on a fault with a pair of force couples that mimic slip at a point, which is an approximation of slip on a rectangular surface, which in turn is an approximation of slip that varies spatially and in time. So here's an example of the great Tohoku Oki earthquake that hit Japan. That was like magnitude 9.2. And you can see in this area here, there was slip as much as 30 meters. And then in other areas, there was slip as less than 5 meters. So we can see that the slip and also the timing of the slip vary along a fault plane. So things that we want to think about in this lecture are far field pulse shapes, the far field pulse frequency content, and associated phenomena that quantify the nature and strength of earthquakes, most notably the magnitude scale. So we're going to talk about how magnitudes are actually calculated. So first, I want to talk about how slip occurs on a fault. So we'll consider a propagating rupture front. So slip occurs at the hypocenter first, and then it propagates outwards. We can simplify in terms of slip on a rectangular area, and at t equals 0, we have the hypocenter. So this is where the slip begins. And then this, what's the word? This shaded in area is where slip is completed, and the rupture front is where slip is going from 0 to the maximum that it will get to. And this rupture front travels with rupture velocity v sub r. And the time it takes to go from 0 to maximum rupture is called the rise time, and that's tau sub r, or T sub r. So the moment released by an earthquake is going to start out at 0, and then it's going to take from the rise time to go from 0 to the full rupture, and then it is going to follow the rupture time. And the time derivative of the moment is going to look like this. It's going to follow a boxcar distribution. Now we can consider two stations at different azimuths from the fault, and both are a distance x from the epicenter. So the first station is directly in the path of the rupture, and the second station is perpendicular to the direction of rupture. The start of the displacement will arrive at the same time, since the start is the same distance away. But the finish will be at different times. So in this case, the finishing part of the rupture just has to travel a distance x minus L, where in this case, the finish of the rupture has to travel the square root of x squared plus L squared. So the time of the finish is going to be larger than the time to the finish here. However, since the total moment has to be the same, the area of the source time function has to be the same. So what this means is that the direction of rupture is going to cause the intensity of slip to be larger in the direction of rupture and less or orthogonal or even backwards to the rupture. So here's another example. This is a case where rupture is in one direction towards this receiver, and then it ruptures in an opposite direction to this receiver. And we can get the rise time is L over times 1 over VR minus 1 over alpha, where alpha is the p wave velocity. And here the rise time is L times 1 over v sub r plus 1 over alpha. And the displacement pulse can be thought of as a convolution of boxcar functions, where we have one boxcar function that mimics the rise time and another boxcar function that mimics the rupture duration time. So if this was the case, our displacement would look something like this trapezoid here. Now the area under the trapezoid is going to have to be the scalar moment. And if I'm in the direction of fault rupture, the time at which the fault ruptures from the beginning to the end will be contracted. Whereas if I'm in the opposite direction from the fault rupture, the time will be extended. Since the total area has to be the moment in every case, what this means is the magnitude of deformation will be larger in the direction of the fault rupture, and it'll be minimized opposite the direction of fault rupture. We can use near and far field sources to get at m of t and its derivatives. So we have moment in the near field causing permanent displacement. The far field displacement is proportional to the time derivative of the moment, which is going to look like a pulse. And the far field velocity is going to look like the second derivative of the moment. So it'll look like this here. And here are two sort of older studies, but they show you the source time functions for a 1989 earthquake. So in both cases, they find two areas of higher slip surrounded by areas of lower slip. So this just goes to show you that the slip is not uniform along a fault plane. Okay, so I want to talk about magnitudes and moment. So it's a natural human desire to want to quantify the size of an earthquake. And having a simple way to convey earthquake size is also useful. Using the observation that the amplitude of seismic waves is proportional to the earthquake size, a series of scales have been proposed with a common form. Magnitude equals log of amplitude over the wave period times some factor that corrects for distance and source depth, plus a source correction, plus a receiver correction. And the most basic type is we just take the amplitude of a P wave, divide that by the wave period of the P wave. Typically, we just do it at 1 second. So then we just take the amplitude, and then we modify that by a factor that has been empirically calculated that takes into account things that do not affect, are not related to the earthquake size, such as regional attenuation. So scatter and M sub B from different stations from the same earthquake can be as large as 0.3 magnitude units. So averaging is employed. So it's worth noting that through this body wave magnitude, we don't get the most precise measurements. We can also look at the surface wave magnitude, and for reasons that I will discuss shortly, this is better for larger earthquakes. And this is based on the maximum amplitude of the Rayleigh waves. And typically we use 20-second Rayleigh waves. And so a formula for the surface wave magnitude is log base 10 of the amplitude of the 20-second Rayleigh wave plus 1.66 times log base 10 of the distance plus 2.0. So a problem with these magnitude scales are that they're kind of ad hoc, right? They're created to fit past magnitude estimates, and like the plus 2.0 is just sort of an arbitrary fudge factor. M sub B and M sub S will give different values for the same earthquake, and M sub B and M sub S will saturate, which means they will underpredict the size for large earthquakes. So we can look at the Alaska 1964 earthquake, which the body wave magnitude was predicted to be 6.2. The surface wave magnitude was 8.4, and the actual moment magnitude, which I'll get to shortly, was 9.1. And this is the accurate magnitude right here. So this is because a large earthquake produces P wave amplitudes of the same size as a much smaller earthquake. So our best option is to use the moment magnitude, which whether you have your moment in Dyne centimeters or Newton meters causes you to vary this equation somewhat. And it's based on the work done at the fault, and it doesn't saturate. And it takes, a disadvantage is it takes more effort because you actually have to sum the total moment at all seismometers that you can get at. And for small earthquakes, M sub B and M sub S are just about as accurate. So to understand why the body wave magnitude and the surface wave magnitudes do not work well for large earthquakes, we need to think about the source spectra. So we've discussed earlier that the source time spectrum of an earthquake can be approximated by the slip function, kind of shown as shown here. And this can in turn be represented as the rupture time convolved with the rise time. So the first derivative of the moment looks something like this trapezoid. Now in a spectral domain, a convolution becomes a simple multiplication. So we've talked about that already. So the convolution of T sub R and T sub D can just be multiplied in the frequency domain. And now let's approximate the spectrum of a boxcar, or no, let's not approximate. We do know that the spectrum of a boxcar with amplitude 1/T is the sinc function, and this is actually spelled wrong, it's SINC. And the sinc function looks like this here. The same formula applies to T sub D. So this boxcar looks like this function here. And then the spectrum becomes this. And we can take the logarithm to get the amplitude equals log of m naught times the log of these two sinc functions. And now what we're going to do is make an approximation. So it is not the most accurate approximation, but it turns out to be quite useful. So we're going to say sinc x, which is sine x over x, and looks like this near x equals 0. We're going to approximate that by 1 for x is less than 1, and 1 over x for x is greater than 1. If TR is greater than TD, so the rupture time is greater than the duration, we can divide the equation up into 3 segments. So omega is less than 2 over the rise time. Then sinc of omega times T sub R over 2 is going to be equal to 1, and sinc of omega times T sub D over 2 is going to be equal to 1. We're using this approximation that we developed in the last slide. And that means the log of amplitude is going to be the log of the moment. If omega is between 2 over T sub R and 2 over T sub D, then this here is actually going to be 2 over omega T sub R, where the duration is still going to be equal to 1, the sinc of it. So the formula for A sub omega is going to look more like this here. Finally, if omega is greater than 2 over T sub D, then our amplitude looks like this here. So in our approximation, we now have log of A of omega equals log of m naught for omega is less than 2 over T sub R. And then it equals to this for omega is between 2 over T sub R and 2 over T sub D. And then it's this for omega, which is greater than 2 over T sub D. So if I plot the amplitude as a function of frequency versus log of angular frequency, we're going to see something like a slope of 1, a slope of 1 over omega, and a slope of 1 over omega squared. So Also, it's relevant that rupture length tends to increase with magnitude. So both the rupture time and the rise time scale with the rupture length. So as T over R increases with larger earthquakes, 2 over T sub R will decrease. And 2 over T sub D will also decrease. It should say decrease here. So what this means is as our earthquake gets larger in size, these corners here move to the left. And the point at which log of A of omega starts to roll off, so the point at which we go from a slope of 1 to a slope of 1 over omega is going to happen at lower and lower frequencies. So what this means is our spectrum will change with the total moment. And so for the lowest frequencies, we can directly measure the full moment of the earthquake. But for higher and higher frequencies, for instance, for a body wave, we reach this area where the spectrum rolls over and we just get a maximum amplitude for body waves. So that's why these larger earthquakes, as shown here, will produce a body wave magnitude of 6.0 and a surface wave magnitude of 8.0, even though they're in real life, they're a moment magnitude of 9. So in real life, finding the corner frequencies can be difficult, and the theoretical spectrum is dependent on the faulting model, and results are dependent on the attenuation correction used. But we can see that the frequency versus the moment does vary with, it goes down with higher frequencies. So what we've done is we looked at some magnitude scales. We looked at the body wave scale, the surface wave scale, and what I suggested is the most accurate is the moment magnitude. And that's because the amplitude spectra of an earthquake source is flat for low frequencies, but it rolls off for higher frequencies. Whether there's 2 corners or just 1 depends on your rupture model. We used a model where we had 2 corners, and that's because we had a convolution of 2 boxcar functions, one for the rise time and one for the rupture time. We showed that the corner frequencies are proportional to 2 over T sub R and 2 over T sub D. And these move to higher frequencies with, they actually move to lower frequencies with higher moments. And since rise time and rupture time increase with moment. So the consequence is that at higher frequencies, A of omega doesn't change much with increasing moment. So we have saturation. So saturation occurs first for body wave magnitude, which is recorded at 1 hertz, and then at surface wave magnitude, which is recorded at 0.05 hertz. And calculating the moment magnitude solves this problem. However, for small earthquakes, M sub B and M sub S are easy to calculate, so we still use them. All right, any questions on that?
I have a few questions. You said 20-second rally wave. What does that 20-second mean?
So that's the wave period of a Rayleigh wave. So what we would do is, if we observe a Rayleigh wave at a seismic station, we can create a bandpass filter, which filters out frequencies that are not 0.05 hertz or 20 seconds. and then we will just get the amplitude of the 20-second component of the Rayleigh wave.
Okay. So there could be 10 seconds, 5 seconds, everything. Like how many? What's the range?
Yeah, so Rayleigh waves are typically observed from 5 seconds to roughly 150 seconds for a teleseismic Rayleigh wave. But 20 seconds tends to have the largest amplitude, which is why we use that.
Okay, and this rupture front that you're talking about, is this on an existing fault or is it a new rupture on a intact rock?
It's on an existing fault.
Oh. So during the earthquakes, do you think new faults are created, or is just the same fault that has been slipping for millions of years? Is that the only fault that's slipping?
I think generally it's on existing faults. We actually see in Colorado, Precambrian faults have been reactivated. So faults as old as 600 million years old can be reactivated. And that seems to be a lot easier to do than to create a new fault.
Okay, okay. And also, what are the types of software that you are using for your for these simulations? Is it like a Coulomb software, or is there something more advanced like these simulations that you can do?
To calculate the source spectrum or the moment or what?
Yes, the source moment, and just like a general picture of a simulation. I mean, if we want to see that in real time, or maybe a simulation of the fault slipping, let's say we use some inputs of the stresses and the fault angle and the fault friction coefficient, a lot of those things, and then we want to see how the fault is moving, like a it's just like a simulation of a real-time simulation. How would you, which software do you use? Just like
Well,
I'd like to see the movie of the earthquake happening, given the inputs that I have.
Well, one option to actually simulate ground motion for a earthquake with a given focal mechanism is called SpecFem.
True.
Another one is called AxisM, and that's a Python module. And then if you want to actually measure the source time function of an earthquake, you could use something like SAC or MATLAB or Python to actually calculate the spectra. And then there are simulations or programs that will calculate the stress change due to an earthquake. I'm not too familiar with those though.
Okay. Okay. Just one unrelated question. I was thinking that we would have lectures for maybe next 2 or 3 more days, but you said today is your last lecture, so I was just wondering why.
Oh, and then Mohit will lecture.
Okay. Okay. Thanks.
And I will do the next tutorial as well.
Okay. Thank you.
Any other questions?
Good morning. Hello, sir.
Yes.
Sir, in one slide, you showed SP phase is negative. Like and we are discussing about phases here. In one slide, SP phase showing negative polarity.
Yes, because it's a bounce off the free surface. So the little s big P and the little p big P will have a negative polarity, whereas the direct P will have a positive polarity.
Okay, that free surface only is showing that it's a negative polarity. Is there any direction of propagation affects that phase?
I'm sorry, I didn't quite catch what you said there.
Only reflection from free surface only affecting polarity, or
Yes.
direction of propagation is also affected because S and P are there. So
Yes, that's true. So the direction it leaves the earthquake is also plays a role.
Okay. Okay, sir.
Any other questions? All right, let's take the rest of this time to work on any homework. I'm going to go get a drink of water. I'll be back in 2 minutes. I'm just curious, are you all working on your homework or have you finished your homework? I see. Thank you. Any questions before I go?
Thank you, sir.
You're welcome. All right, I will see you all tonight, and we will work on a second phase of GMT programming. See you then.
See you, sir. Bye.